DeepResearch has been recreated in open source. So here they train agents to reason, and within reasoning to search web, retrieve results, then continue reasoning to do multiple other searches, and then report the result at the end, just like deep reasoning from Google OpenAI DeepResearch, sorry. And the difference between this and other open implementations is that this one is actually trained with reinforcement learning to better learn to use search, while others are just hard coded or have prompts and are just built like that, stitched together. So here we can see some results. So first, the dark blue is the Qwen32 instruct that was fine-tuned with reinforcement learning to do this, and this one is same model but not the instruct version. And then we have a naive generation. This is just asking the LLM to answer these questions, and the questions are pretty difficult. The questions are like, who was US president while when DeepMind was founded? And so there needs to be like multiple searches and stuff. So we have these like two naive RAG, naive generation, and then a bit more advanced methods, but they all lose to our instruct and the base Qwen32B models. You can help me do my videos full-time, Patreon link below. The way it works is the model is using think tags to think. It's also using search tags to write a query, search query into these tags. When it writes this search query, then the system will automatically perform a search and retrieve results. And then the results will be shown to the model with results tags. Then model will continue thinking. It can also create search tags as well to search for different things. And when it feels it's finished, then it can generate answer tags and give its answer. They are using GRPO that was used to train a DeepSeek R1 that was invented by DeepSeek for reinforcement learning, and they're going to train these two models, Qwen 2.57b and instruct version of it, and 32b and instruct version of it. So these are one of the most powerful open source models currently. So the trained models with reinforcement learning get 8.9% to 22.4% improvement over the baselines. So I'm guessing the baselines either means the LLM generates answer directly, or it can use a simple web search. We'll see what these baselines are, but whatever they are, this is a big improvement. Let's see a bit better how it works. So first, it gets some query. Who was the president of the United States in the year that Citibank was founded? So let's skip all of this. Let's ignore this. Let me just show you the what's happening inside the model. So first it's thinking. To answer these questions, I need to do this. Closes think tags, opens search tags. When was Citibank founded, for example? Closes search tags. As soon as these search tags are closed, there is a system that's going to automatically that stop the model and search for this, and then it will return results, and then it will put those results into results tags and just append or concatenate to the current model generation. Then the model will continue thinking. I believe they can either put these tags, open the tags automatically, just insert it there, or they can let the model choose if it's gonna open tags. And then we continue the process. So those would be two types of training they could do. We'll see maybe later which one they did, but it's not so important for now. And in the end, model will choose to put the final answer into the brackets and close these square, or not square, these kind of tags. So let's see how it works. So it starts from this query, and then the general tasks it has is generate till search or end of sequence. So this is the final end after it generates answer closing tag. It can also retrieve search result and concatenate the search results with the current generated text and continue. So this is just a broad overview. So we start from the prompt. LLM policy just means the LLM model. So when they say policy, they just mean the LLM and nothing else. So it's generating these like think, search stuff text. Then when it closes these search tags, it goes, so here it's gonna show you like the output rollout thing, but we already understand this. So here, when it closes the tags, it will do search. The system will do search, return result, and feedback to the agent. And this will repeat, repeat, repeat. So this is that rollout that's gonna happen. And then we have up here the GRPO algorithm. So this first block that you see here, I already explained it here. So this is the same block, this big block. So it starts from the question. There is this LLM and search. It's circling. So then it will produce one rollout. So rollout is a whole like reasoning search with the answer in the end. Okay, so one rollout. Second, independent rollout with second answer, sorry. So question is always same. We just produce multiple answers, and each answer is like this, has the entire thing here. So so we can later use reinforcement learning to find the best answer and the worst answer and tune the model. Okay, so once we have a number of possible answers, number of sampled answers, we are going to calculate, let's start with here, calculate reward for each answer. So we will get a list of rewards. This reward is calculated based on if the answer here in box this is correct, and if it follows this structure with these tags. And the answer being correct is more important, and the reward weight is higher there. It will get more reward, or more reward will be subtracted. What is this KL divergence? So it's also important that if these answers or rewards are like crazy, they don't accidentally change the model too much if these numbers are huge for some reason. So KL divergence is going to limit how much the model is going to change, so that there is no like one rogue case that messes up the whole model too much. It's also going to just make the whole updating process more stable, and just gonna limit it so there is no like too much change. So this is important. We know that this is using GRPO algorithm, and the one advantage is that of that algorithm is that you don't need to train a separate AI that's going to be like reward model, that's going to reward this AI for doing good or doing bad. So like PPO, proximal policy optimization, it needs to train a different AI for reward, and now you need to give it compute, and you are not using that compute for your LLM training, etc. So DeepSeek came up with this, and the main idea here is you see all of these scores, and then for each of the scores you compare how does it compare to every other score. For example, the best score, it will reward the model to reinforce that kind of like decision making and token generation that produced the best score, and it will not reinforce decision making that produced the worst score, for example. So the main idea behind GRPO, group relative policy optimization, is that it looks in the group, compares to other results, each result to other result, and based on how each result compares, it's going to update model strongly or not so strongly to reinforce that type of token generation that led to good results. But in this step, we are just calculating rewards. And then in this step, we are comparing rewards with all of the other rewards. So for each of the rollouts, each of the answers, we calculate advantage. Advantage shows how much this particular reward is better or worse than the average. And that's shown in this term advantage. And it will use advantage to decide to either reinforce or not reinforce the process that led to this output. This math formula seems crazy, but that's just what I explained. This is the formula for GRPO. That's what I just explained. And this is a fun fact. So this will keep generating the result until it encounters end of text or IM end. So these are the end of sequence tokens for these models. It's just a fun fact. This is like not related to this paper. This is just like how the models are trained. This means like I finished my answer. Another thing with GRPO is you want to have a very distributed and wide-ranging rewards. So you want to have maybe 2-3 really high rewards, so GRPO knows to move towards them. Maybe 1 or 2 really low rewards, so GRPO knows what's really bad, and also rewards in between. You don't want to have all rewards pretty similar, because then it's gonna be harder for GRPO. It's not gonna be as clear where to go, what kind of changes to make. And so when they are using GRPO, they are masking or ignoring all of the tokens within these result tags, because they are not generated by the LLM. So they are ignoring them, and they are just reinforcing tokens generated within thinking or search tags. So it was a little bit confusing to me as well. So if they are ignoring this content within results when updating policy, then for these tokens, it doesn't make sense to me. Like, these tokens are being updated while this is being like, they can't look at this or something. I didn't understand completely. So how does ignoring these tokens influence teaching model how to generate these tokens while not letting it see these tokens? So it didn't make sense. But in reality, the updates on weights that produced these models don't depend on seeing this content. They just depend on getting the correct result. So, but I'm still trying to wrap my head around it, because we are updating these to generate these actually without result. But what if the result content is not good? Then it could cause mess here as well. But I guess from my understanding is it doesn't make sense what the result content is. These will always like be as good as possible given any result content. But I don't 100% understand it. Reward modeling, they are rewarding for the correct answer, and they are rewarding if the model is following defined structure that's defined here. I'll show you. And if there is this boxed answer in the answer tags that shows the result. In the prompt, they just describe think answer tags, search tags, and result tags, and then they give an example. And then they say that it must have this boxed text within answer tags, and put the final answer here. They also create a bit different prompt for instruct model. Instruct model has been trained on top of this based just pre-trained model. Instruct model will know how to generate talk to user in messaging format, where it waits for the message and then generates the response, while this base model is just rambling text. It doesn't know. So here they are giving it prompt and then specifying user, inserting prompt, and assistant, so it will understand that it needs to generate assistant reply. While here its instruct is already trained to generate assistant, so they don't need to like specify like this what to do. So for the final reward, if the answer is correct and format is correct, 0. If answer is wrong and format is correct, then 0.1. And if answer is correct, then just the answer reward. So A prediction and A ground truth, and this is F1 score between these two. This is how the F1 score is calculated both the predicted answer inside the box tags and the ground truth answer are broken down into individual words tokens, usually after lowercasing and removing punctuations. Then measure how many of the tokens from the predicted answer are contained in the ground truth. Then also measure vice versa, how many tokens from the ground truth are contained in the predicted answer. So this is how many correct words were predicted, and the previous one was how many predicted words were correct. So we got this formula for F1, which is going to be 2 times precision plus recall. Precision is the first, recall is the second thing I explained, and divide by the sum of them. And the answer will always be between 0 and 1 because these two, precision and recall, will be between 0 and 1. And that's what I asked it here, and it explained Gemini Pro, the new one. Let's understand this formula intuitively. So, multiplying them, joint success. Multiplication will only give high number if both values are high. So if one value is high and the other is low, then it doesn't matter that this one is high, the result will be really low. Here you can see example real quick. So this multiplication says, I don't care if you can just recall or you just have good precision, you need to have both of them good to get high score. Then what this sum does, it just makes the multiplication not produce a huge numbers. So it just scales down the numbers. And usually in machine learning, it's good to have numbers between 0 and 1. That will just improve learning. But even though we have this scaling down, we are going to still multiply the numerator with 2. So the numerator with 2. So because if we didn't, then the maximum number would be 0.5. Because if both of them are 1, so you get 1 over 2. That's 0.5. So this will bring the maximum to 1. And so we will have 1 over, we will have 2 over 2. So why don't we just multiply precision and recall and then get value between 0 and 1? If they are 0 and 1, why do we need to introduce scaling back with the sum and multiplying with 2? That's because that lets us be more sensitive to low numbers. So if we do it in this F1 way, then if one of these is low, this result will get low and it will be punished. So the harmonic mean, which is our F1, penalizes imbalance between P and R more harshly than simple multiplication of the arithmetic mean or the arithmetic mean. So they are benchmarking, evaluating on more difficult questions that cannot be answered just by a simple search with search engine. For evaluation metric, they use both exact string match, where they compare if the result is exactly the same as the ground truth, and if it's not, they have this LLM as a judge, GPT-4o mini as backup, that's going to look at the ground truth and the result and see if the result is correct. This is if the result is given in a bit different format, but it's still correct. They are using almost 20,000 samples for training for 2 epochs, so the model sees these 20,000 samples 2 times and trains on them 2 times. But I think they use LLM as a judge for every single case. They don't first compare it with string, but I think it would have been better to just try to string compare, and if it fails, then use LLM as a judge to check again. So the average improvement is from 15 to 17, 18% on average, which is actually a lot of improvement for these benchmarks. And this is for this model with the 7B parameters, and kind of the similar, a bit worse improvement from 14.8 to 15.4% for the 32B model. So the improvement is pretty good in both cases. They also find that in training on top of instruct model works better than training on top of a base model. For this case, now I wouldn't say this is necessarily always true. I think the more training you have, the more samples, the better it is to use base model. But I think just that might not be true. So maybe they don't have too many examples here, like only 20,000. So instruct model is going to work better for fewer examples. So in the training, the model really learns to generally use search. So even though they just trained on this single dataset, which I believe is connected to a single benchmark, it performs better and improves on all of the other benchmarks that use this multi-search reasoning process. So here we can see results. So for the baseline, they are using instruct model, and they are plugging instruct model, 7B in this case, into these four baseline methods. So this is just asking the question, this is just doing one retrieval, and these two are more complex. And then there is the same model fine-tuned with their method. So this is the base model fine-tuned, this is instruct model fine-tuned. And we see that instruct model has the highest scores in the group for all of these four different benchmarks. And EM is exact match, exact string match, and this is LLM as a judge. So LLM as a judge has higher percentages because this thing probably generates a good answer, but it's not in the exact string or format, so the string match doesn't work. So that's why you should trust LLM as a judge more, I believe. And we can see the same for the 32B model. It outperforms every other method. And some methods, if we look at LLM as a judge, this is a big improvement. Here you can see that as the training is progressing, the response length is increasing. This means that the model is using search more, making more searches. And I will show you up here. So this is the dark one is the instruct 7B, and the dotted dashed one is the quen 7B. So the response length is increasing for all of the models. And same for number of searches, it's increasing for all of the models during training. So model is learning how to do more searches and how to improve the answer with more searches. Maybe here towards the end, it learns, okay, maybe I don't need this many searches. I maybe can solve this with fewer less searches. Here is the reward model is getting during the training. So as the training goes on, the model is getting more reward. And you see this in the background, these like very faded, very sporadic lines. I think this is the actual reward. And this dark line is just a smoothed version. So I want to tell you that if you see like very sporadic reward in your training, in reinforcement learning in any case, don't be panicked if it's like shifting like crazy up and down, because from what I can see, it's always, not just here, but it's always shifting like crazy up and down. But it needs to increase slowly, and this is good. And it's slowly increasing for every case, the reward during the training. This is an interesting case. So there is one question, and it needs to find in which country this guy is a politician in the first step. And then it's going to see who won in 2018 the presidential election in that country in which this guy's political party operates. So in the first, so it thinks, then it searches for this guy, but what happens is that result doesn't show anything related to politics and doesn't show any good results. So it says, it appears I made a mistake. I need to search political party of this guy. And then it searched it, and then it got it, and so it progressed, and the final answer was correct. You can check it here. This is the correct answer. So they observed this reflection phenomenon. I made a mistake, where the model recognizes that it made a mistake in the search query. They didn't explicitly teach it how to do this, it just learned on its own. Help me do this full time, guys, by supporting me on Patreon. See you in the next video.